Okay, so this is the first example now that has friction involved with it. And just before this example, we meet a little bit about how we're going to calculate friction. So the maximum amount of friction that we're going to use is calculated by using mu r. This is sometimes known as F max, or sometimes it'll say that the friction is less than or equal to this value. Generally speaking, you'll just use this in calculator, but you need to be aware that you won't always have to have this most amount of friction that we use. Okay, so tension actually is increased to 10 apparently, so this 5 actually becomes 10. We've also got to label our vertical forces, so we've got our 10G going downwards and our reaction force going upwards. So you'll see in this friction formula, reaction force is how we're going to calculate the friction. The amount of force that the object exerts on the ground, there's going to be a bigger force that the ground exerts on the object, which is the reaction force. So that will increase the friction, that amount of pressure, more friction. And the mu is our coefficient of friction, so how frictionless, how rough the surface is. It's between 0 and 1. So in the first part it says the tension, as I said, is increased to 10, but it remains at rest. So if this is the bigger force, that means that friction is going to be kind of going this way. So in part A, we need to look at the vertical forces. So you can do this as an F equals ma. So R going upwards minus 10g. But this object is going to be, if anything, moving along the surface. So the acceleration will equal to 0. So if that's equal to 0, R minus 10g is 0. Might go straight to that step, and R is therefore equal to 10g. Because this object is in equilibrium vertically, i.e. it's remaining at rest, you could just go straight to the forces upwards equal the forces downwards. Some people will do that. If we then look at the friction, so using this formula, our friction will equal to mu, which is 0.2, times by 10g. Friction equals, that's going to be 2g, which is 19.6 newtons. Then if I look at what the forces are doing going this way, so as an F equals ma, or just looking at the forces, we're trying to show it's remaining at rest. So we've got a 10 Newton force going left, we've got a 5 Newton force going right, taking it off, and also taking off this 19.6, which is friction. Now, because this is a frictional force, so the 10 minus 5, if we didn't have the friction, this object would be accelerating left. And if this was a force going to the right that was something other than friction, so an active pulling force or a pushing force, this would then be either accelerating to the right or decelerating to the left. But because it's a frictional force, this force can only stop things happening. It can't actively accelerate or move things the other direction. So this means that because this is less than 0, I won't even do the full F equals ma, the object is going to remain at rest. If it was already in motion, this would be slightly different, so we would calculate the F equals ma and it would be slowing it down. But because it starts at rest, this force here isn't actually going to start able to move it the other way. Okay, so it's only a stopping force, but if it's stopped already, then can't do much else other than stop it moving. Okay, if we look at part B, and I'll do a new diagram possibly for part B up here. The space that we've got. It says the tension in the right string is then increased to 30 newtons. There's no mention of the left string, so we assume that's still 10 newtons. And there's no mention of the other forces vertically, so that means that R and 10G are still going to be working vertically. And then increase to 30, show the block moves. Now, if the block is moving and this force here is bigger than this force, this means the friction is going to be going this way. Okay, so you just need to think about what might have changed and what might have stayed the same from the earlier part of the question. So first of all, if you think about the vertical forces, nothing has changed here. So R is still equal to 10G, and therefore that means this calculation of friction is still equal to 19.6. The only difference is the 19.6, suppose that's newtons as well, is now going to the left. So we're just going to look at the forces, the F equals ma, going to the right. because that's where it is having the bigger forces. That's 30, 20 and just under 20, sorry 10 and just under 20, so it's just under 30. So I've got 30 newtons minus 10 newtons minus what we know is 19.6, and that is equal to 10A, so that's the MA. Okay, now you could calculate what this number is. I think it's 0.4, or you could type it on your calculator and divide it by 10, which is probably what I am going to do. I'll get my calculator. 30, take 10, take 19.6. 0.4 divided by 10 to 0.04 meters per second squared. One thing I would always advise against is, notice here when I said you could in theory go straight to the equilibrium, so this equals to this. It wasn't really relevant for this question because we were trying to show it didn't move, but in this direction here where motion is possible and in part B becomes actual, I would never do just left equals right personally. I'd always be thinking about F equals ma, even if it remains at rest, because again, you want to be prepared for doing that kind of motion. This direction here is very rarely, when you've got a reaction force, very rarely going to have any motion. So you only have a reaction force when an object is in contact with another surface. So there's only a very limited number of scenarios where we have a reaction force and motion, because the object then is going to have to stay in contact with the surface. That's a contact force. The main one is like a lift, because the object can remain in contact with the lift, but the lift can move as well. So generally speaking, your R direction is in equilibrium, other than if the surface it's on is moving as well, like a lift.